Pre-feasibility analysis of energy efficiency measures for buildings and factories with RETScreen Expert. Part 4. Reconciling RETScreen fuel consumption with historical utility data. In the previous videos, I've explored RETScreen's Energy tab for the archetype of a metal fabrication plant. In this final video, I'll look at how to adjust the parameters describing the facility in order to reconcile the description with the measured utility bills for electricity and gas consumption. Let's say that over the course of a year, I've collected the monthly utility bills for a metal fabrication plant in London, Ontario. I sum them to arrive at the yearly totals for gas and electricity consumption. I compare these totals with the base case fuel consumption from the comparison table for the archetype and find them to be different. What should I do? How should I adjust the Energy tab inputs to better align the model with reality? I need to start by recognizing that the archetype is currently estimating heating and cooling loads based on climate data, which reflect long-term averages, but the utility bills are from a particular year and may have been influenced by weather during that year quite different from the long-term climate norms. To make the model output comparable to the utility data, I should normalize the utility data. That is, using the performance analysis functions of RETScreen Expert, I should develop a statistical model that predicts energy consumption based on weather data, and then apply that statistical model to the climate norms. A different approach is simply to overwrite the climate data on the Location tab with the monthly weather data for the year when the utility data was measured. With this second approach, bear in mind that the output is now for a specific year, not a typical year. Similarly, I should identify other potential factors of influence, that is, exogenous variables that could be affecting the energy consumption, and extend to these variables the approach described above for weather. For example, for a metal fabrication plant, energy consumption is likely to be affected by product throughput or the number of work shifts. I could extend the statistical model to predict energy consumption based on not just weather data, but on these variables as well. Then I could normalize the utility data to reflect typical production throughput and typical numbers of shifts, as well as typical weather. Let's say I've done this normalization process and come up with the typical natural gas and electricity consumption. Imagine that according to the utility bills, these should be 90,000 cubic meters of gas and 2.7 megawatt hours of electricity per year. I'd go to Comparison on the Energy tab and enter these numbers in the historical column of the project verification table. Assuming that I'm expecting the base case to correspond to the facility as it was when these utility bills were collected, I'd set the fuel consumption to base case. The so-called variance in the column at the right of the project verification table shows the difference between the Energy tab base case and the historical energy consumption, expressed as a percentage of the latter. In this example, both the natural gas and the electricity consumption estimated by the Energy tab are about 15% lower than the historical estimates. I may want to adjust the Energy tab inputs to reduce the variance, an exercise referred to as reconciliation. How should I go about doing this? First, understand that this is what engineers would call a grossly underdetermined problem. That is, I am trying to solve a mathematical problem with many input variables, but only two knowns, the natural gas consumption and the electricity consumption. An underdetermined problem like this will often have an infinite number of solutions. In other words, there will be an infinite number of ways to set the inputs on the Energy tab that will result in the variance being zero. Despite all these solutions being of equal mathematical merit, there are ways to set the variables that are in reality a more accurate representation of the facility than others. Having a variance of zero does not, therefore, tell me that the model is accurate. Despite this, I will still want to reduce the variance by adjusting my inputs. If the variance is large, then I know that my energy model is not accounting for everything in my real building. If the variance is small, then the model may be close to describing how my facility really uses energy. And if I cannot get the variance close to zero without configuring the inputs in some obviously unrealistic way, then I know that I am missing something. Either some of my assumptions about the facility are wrong, or some elements are missing, or have been double counted, or perhaps some of the assumptions built into RetScreen are not appropriate for this particular facility. When choosing which input variables to adjust, I should always keep in mind my reason for creating a model on the Energy tab. Generating accurate predictions of the facility energy consumption is not generally my goal. Rather, I'm using the model to evaluate the cost-effectiveness of different investments in clean energy technologies. I should, therefore, focus on improving the accuracy of the model where it will help me make better decisions. Let's say I'm uncertain about how much insulation is currently in the walls or ceiling. Should I invest a lot of time and effort to determine the correct R values in order to improve the model? If adding insulation to the walls or to the roof is not on the table for practical reasons, then no, I shouldn't, because it is unlikely to make any difference in the conclusions I draw. Also keep in mind that the impact of inaccuracies in my choice of input parameters will tend to be attenuated when the same inaccuracy appears in both the base case and the proposed case. Imagine that my goal was to determine whether high-performance doors were worthwhile. If I am in error with my estimate of the wall and ceiling R value, but this same error appears in both the proposed case and the base case, then when RetScreen calculates the energy savings by finding the difference between the two, these errors will cancel, and I will be left with the savings due to the differences in the door properties. Having said that, start your modifications to the archetype by eliminating obvious departures from the real facility. For this metal fabrication plant, even during a first walkthrough, I would generate a rough list of the main equipment in the plant, the building dimensions, the operation of the heating and ventilation system, and occupancy periods. I'd want to have those reflected in the Energy tab. Let's say that the real manufacturing plant has a larger footprint than this archetype. I'd go to the building envelope and make the necessary changes. I should remember that if the dimensions change, then the infiltration may also change. I can save myself a bit of time by using the buttons at the right to copy the base to the proposed case. I can extend this approach of adjusting the archetype to match identifiable building characteristics to other sections of the building model. I may want to focus my efforts where most fuel is being consumed. For this archetype, I might be unsure whether my time would be better spent improving my estimate of the cooling system coefficient of performance or my understanding of the process in mechanical equipment. Looking at the energy savings section of the dashboard and the base case fuel consumption in the end-use pie chart can help me with this. From these, it is clear that process electricity and mechanical equipment are far more important than space cooling. Indeed, the cooling load could be an order of magnitude larger than in the Energy tab, and the impact on results would still be minimal. Note that if you are wondering what is included in an end-use category, simply hover the pointer over the text in the listing below. In mechanical equipment, for example, RetScreen is including pumps, fans, motors, compressed air, and, in the proposed case, the pump for the solar water heater. Realizing that the cooling system is not likely to be a major influence on the electricity consumption, I might take another look at the process electricity loads and the mechanical equipment. I might want to pay particular attention to the amount of time that different loads are operating. This is often harder to determine than the operating power requirement, but it can have major impacts. For example, currently the model assumes the compressed air system operates 90 hours per week. But if I discovered that in fact the compressed air system is rarely shut off, such that it operated 168 hours per week, the electricity consumption would increase by 70 megawatt hours per year, even though most of the time the only load was leaking air. Perhaps I would also find that I'm missing some major electric loads. Let's assume that these include a dozen 10 horsepower motors for conveying parts. I'll add these. I should check to see how heavily they are loaded and how many hours per day they operate. I'll also have to give some thought to how much of their electricity consumption ends up as heat within the building. Given that there is no cooling within the manufacturing area, I'll set the space cooling impact to 0%. For the space heating impact, it is not so clear. Note that it can have a major impact on natural gas consumption. When I set it to 0, my natural gas consumption variance is around -4%, but when I set it to 100%, it is -27%. I'd want to give careful consideration to where the heat from these motors and the other major electrical loads would go during the heating season. For example, if they are located near where air is exhausted from the plant, only a fraction of their heat might end up reducing the plant heating load. For this example, I'll set it to 50%. When adjusting the archetype to match the measured utility consumption, I must not forget the schedules form. I should check the occupancy data as well as interior temperature set points. For example, I should make sure that the thermostat settings are as indicated during unoccupied periods. Here I'll assume that they are not, and set the base case space heating temperature during unoccupied periods to 21 degrees Celsius. Now the variance for the natural gas consumption is -15%. Finally, on the schedules form, I can adjust the heating-cooling changeover temperature. I should do this only once I have represented the characteristics of the facility as accurately as possible in all other forms. Raising the heating-cooling changeover temperature raises the heating demand and lowers the cooling demand. I can watch this happen on the dashboard energy savings bar graph as I raise it from 15 to 17 degrees Celsius. With this change, the variance is nearly zero for both natural gas and electricity consumption. Clearly, the heating and cooling changeover temperature is a significant determinant of the heating and cooling load. In this case, I could change the heating and cooling changeover temperature to match the natural gas consumption without much concern for the cooling load. When heating and cooling are both significant, the range of workable values for the heating-cooling changeover temperature will tend to be more restricted. If it is moved too far in one direction in order to reconcile the heating fuel consumption, the impact on the cooling will be unrealistic, and vice versa. Thus, the heating-cooling changeover temperature cannot be used in isolation for reconciliation. Other model parameters will need to be adjusted. Once I have reconciled the base case with the utility data, I should make sure that my proposed case matches the base case parameters wherever I am not planning to implement a modification. I've been doing that as I go along. Having done that, I can evaluate the impact of the proposed case technologies. This completes this series of videos on pre-feasibility analysis of energy efficiency measures for buildings and factories with RETScreen Expert. For more videos on how to include various energy efficiency technologies in RETScreen, consult the e-learning channel.